faithfully sharing insights and exploring great books worldwide.
Hello, this is Sally with the Book Talk.
Today, we're diving into the book The Last Stargazers. The subtitle is The Immortal Stories of Astronomy Adventurers. Whether called stargazers or astronomy adventurers, they're all astronomers. This book tells astronomers' stories and why the title uses last as a modifier. The author didn't explain it, but I'll give my interpretation after covering the book's content. The author, Emily Levesque, is a real-deal astronomer with notable academic achievements. She's an astronomy professor at the University of Washington, studying massive stars, and has won awards like the Annie Jump Cannon Award and Cottrell Scholar Award. And her book, The Last Stargazers, is a popular science work with autobiographical touches. The author shares her experiences to describe how astronomers work, especially using large telescopes and gear for observations. After publishing, it was loved by readers, became a 2020 Amazon US Best Book, and got praise from experts.
British astronomer Jocelyn Bell Burnell said it's so brilliant you can't put it down.
I'll distill three aspects from the author's story: what astronomers are like, how they observe, and what challenges they face. Okay, let's join the author on this stargazing adventure.
First topic: what kind of people astronomers are?
Let's take Emily herself as an example to see how an astronomer grows and works. For Emily, born in the 1980s, her decision to be an astronomer came from family influence. In 1980, famed American astronomer Carl Sagan released a popular science documentary on the universe, loved globally. Inspired by Sagan's work, Emily's parents developed a deep interest in astronomy. Her dad saved up for a home telescope, and her librarian mom stocked up on Sagan's books. According to Emily herself, astronomy was already part of daily life when she was born, but what truly captivated her was a major astronomical event in 1986. The appearance of Halley's Comet on Earth, which occurs every 76 years, is a once-in-a-lifetime opportunity for many. So when Halley's Comet returned that year, it sparked a nationwide stargazing craze, and Emily's family was no exception. At that time, Emily was less than 2 years old and went outdoors with her family to observe.
Halley's Comet.
Young Emily was immediately mesmerized by the stars in the telescope. From then on, she was deeply devoted to astronomy. Here's a side note. While reasons for becoming an astronomer vary, broadening our perspective reveals that career choices are closely tied to the era's development. In the mid to late 20th century, humanity had immense enthusiasm for space exploration. From the U.S. moon landing to Mars exploration, this period was a peak in human space exploration, with high public interest in space and universe topics. Moreover, the success of science educators like Carl Sagan sparked an astronomical craze, nurturing many people's passion for astronomy.
Naturally, the talented Emily didn't disappoint her dreams. She first got into the prestigious MIT to study physics.
After finishing her bachelor's degree, she went to the University of Hawaii's astronomy program to pursue a PhD. University of Hawaii? Though not widely known, its astronomy program is world-class. It's adjacent to the world-famous Mauna Kea Observatory, situated on Mauna Kea in Hawaii, with excellent geography, over 300 clear nights annually, making it one of Earth's best sites for observation. Countries like the US, France, and Japan have built over a dozen large instruments here, with 2 large telescopes directly belonging to the University of Hawaii. After completing her studies, Emily officially joined the ranks of astronomers. So, what exactly is an astronomer's daily work like? In many people's minds, the word astronomer evokes an image of someone intimately familiar with the stars and able to recount various astronomical phenomena effortlessly. They might look a bit pale, with dark circles under their eyes from staying up late all year, always stationed by a huge telescope. The surrounding papers or screens are filled with trajectories of various celestial bodies. This impression is actually partly right and partly wrong. First, the author sincerely points out that astronomers aren't encyclopedias of the night sky. People often point to stars and ask Emily, "What's that?" At that moment, She can only awkwardly say she doesn't know or, make a rough guess that might not even be accurate. It's like computer science majors don't necessarily fix computers, and civil engineering grads don't necessarily build houses. Without special training, most astronomers can only recognize a few constellations. That's it. Moreover, astronomers don't have to guard telescopes every night. On the contrary, they get very few chances to use telescopes all year. Building an observatory might cost billions of dollars, and running a large telescope for one night can cost up to $50,000. The high costs make astronomers' observation opportunities extremely limited. In some book promotions, there's often this line: Emily has used many large telescopes, with over 50 nights of total observation time. The author, a world-class astronomy grad with over 10 years' experience, has less than 2 months total. Showing how scarce it is. To get access to those big instruments at the observatory, astronomers must diligently submit observation proposals, and the observatory allocates precious time based on research importance and urgency. If luck strikes and they're assigned an observation night, astronomers will embark on a challenging journey. Now, imagine you're such an astronomer. Let's see what experiences you might have. First, you need to get to the observatory. Since they're built in remote wilderness or high-altitude areas with thin air, these spots minimize light pollution and atmospheric interference. 1. As the saying goes, the finest views are at perilous peaks. Getting there means long, exhausting travel, and you constantly pray for good weather. No wind, rain, fog, or clouds on your scheduled night. If you're unlucky and hit bad weather, sorry, you'll have to return empty-handed and resubmit your application. If you get a good night, congratulations, you're in for a busy time. First step: create an observation schedule detailing which celestial bodies to observe tonight, including coordinates, timing, and methods. Then you need a professional operator to assist. This operator controls the telescope, responsible for operating it and adjusting mirrors and instruments. If the astronomer is the navigator, the operator is the actual driver. The operator-driver follows your schedule to find targets in the sky, then controls the telescope to point at the target area. This process requires occasional fine-tuning to lock onto your celestial body. Once positioned, the operator opens the telescope's shutter to begin exposure. The author describes this poetically. Photons escaping galaxies millions of years ago finally land on your telescope, becoming data flowing into computers. After the first target's exposure, the operator turns to the next on the schedule. One target after another. The observation settles into a steady rhythm. Astronomers call this the world's most exciting mechanical work. Sadly, even the most romantic stars can only sustain you until the early hours. After 3 a.m., drowsiness sets in, dulling your mind. As the author says, your blinks become slow, and you'll hunt for any flat surface to lie on. Here, nearly all astronomers give the same advice: play some music. Some observers carefully curate observation playlists, playing different music genres at different night times. Unsurprisingly, these playlists often end with raucous heavy metal rock. Only when the sun rises does the observation night end, letting you relax and drag your tired body back to the dorm. But this isn't the end. The real challenge begins: processing the data. Generally speaking, during observations, you'll get two types of data: imaging data and spectral data. Imaging refers to the night sky images captured by telescopes. From these images, people can learn about galaxy shapes or celestial brightness and other information. Spectral data is more complex. It appears as thin lines because different elements produce lines at specific positions on the spectrum. This data reveals celestial chemical compositions. Whether imaging or spectral, you need significant effort to process and analyze results. During observation, telescope signals contain substantial noise from stray light, moonlight, atmospheric interference, or camera sensor glitches, but 88 occasional noise spots. In short, this noise acts like thick dust covering your desired data. Your task resembles archaeologists handling unearthed artifacts. carefully cleaning surface dust to reveal true treasures. These tasks are just a snapshot of astronomers' daily observational work. So, to gather more information from the night sky, they employ various advanced astronomical techniques. Emily herself visited observatories worldwide to use their large-scale equipment. Each astronomical device has unique characteristics. Next, we'll introduce 3 types of observation equipment Emily used or visited. They are optical telescopes, radio telescopes, and gravitational wave detectors. We'll discuss these devices' features and the research astronomers conduct with each. The most common large equipment in observatories is the optical telescope. Both imaging and spectral data mentioned earlier can be collected through optical telescopes. Its core capability is light gathering power, how well it collects light. Light gathering power relates directly to telescope lens aperture. Larger apertures mean stronger light collection and better observations. For example, in 2017, a project funded by over a dozen countries began building Earth's largest optical telescope in Chile, South America, with an astonishing 39-meter mirror diameter. Here we can also learn about Emily's own scientific contributions, since her most important scientific achievement was accomplished using optical telescopes. Her fortunate observation site is the Las Campanas Observatory in Chile. She used one of the Magellan telescopes there with a 6.5-meter aperture. Fascinated explanatory objects called Thorn-Ziko objects, TZOs, fascinating hybrids with red supergiant shells hiding neutron stars at their cores. Red supergiants are massive stars nearing the end of their lives. These stars have masses 10 to 20 times the Sun's and diameters hundreds to thousands of times larger.
Neutron stars also form from stellar evolution. Solar mass compacted into just 10 to 20 kilometer radius.
This makes neutron star density astonishingly high.
It's estimated a fist-sized neutron star chunk would equal a mountain's mass on Earth.
Both red supergiants and neutron stars are fascinating to study, let alone their combined TZO form. CZOs were theorized in 1975 but never confirmed. Emily's team hoped to find one, guided only by clues about unusual surface elements. In September 2011, Emily went to Chile hunting TZOs. With 3 observation nights secured but little confidence, she tweaked plans until the last day. Fortunately, observations went smoothly with clear images captured. Emily noticed anomalies in a last-minute target's spectral signals. Specifically, white spots appeared where dark gaps should be, indicating unusual atmospheric elements, though she lacked time for immediate analysis. Post-observation, Emily spent over a year meticulously processing the data. That peculiar star noticed during those 3 nights ultimately yielded unexpected discoveries. Specifically, those strange signals indicated this star had far higher levels of lithium, rubidium, and other elements than typical stars. These findings perfectly matched the theoretical characteristics of TZOs. Thus, the star named HV2112 became the most promising TZO candidate ever discovered. Emily successfully gathered first-hand data about these stellar mechanisms. Beyond optical telescopes, Emily also used radio telescopes, which lacked traditional lenses. They resembled giant perforated middle lids made of white mesh, like oversized satellite TV dishes. Radio waves are electromagnetic signals. Earth's atmosphere absorbs cosmic radio signals, but those reaching ground level are called radio waves. China has a 500-meter aperture radio telescope, famously known as the China Sky Eye. In the sci-fi novel The Three-Body Problem, the device receiving alien signals is precisely a radio telescope. This is not a radio telescope. Astronomers study various phenomena with them, observing stellar magnetic fields, hunting pulsars emitting electromagnetic pulses, detecting cosmic background radiation, and more.
In 2017, coordinating 8 radio telescopes globally, scientists observed a galaxy 50-plus million light-years away and captured the first-ever black hole image.
When published, this achievement instantly became headline news worldwide. Emily visited the U.S. National Radio Astronomy Observatory using its telescopes to study peculiar phenomena in red supergiants. There, the Very Large Array comprises 27 radio telescopes, each nearly 30 meters tall and weighing over 200 tons. And radio telescopes differ from optical ones. They work daytime, withstand weather, but fear snow accumulation. Heavy snow can bend or damage antennas, but observatories worldwide have clever snow solutions.
The author mentions one observatory, considering airplane jet engines to blow hot air and melt telescope snow.
But using radio telescopes has precautions, minimizing surrounding radio wave interference. Thus, residents near observatories with radio telescopes can't use phones, Wi-Fi, or microwaves. Beyond optical and radio telescopes, the book introduces gravitational wave observatories. As the name suggests, they detect gravitational waves. Einstein predicted their existence in 1916. General relativity states cosmic cataclysms like massive celestial mergers violently distort spacetime, propagating as gravitational waves. Though extremely faint, to detect these faint signals, gravitational wave observatories were built. The author visited the famous LIGO in the U.S. This observatory has two facilities, each shaped like a giant L. Each L-arm stretches nearly 4 kilometers, encased in thick concrete with 1.2-meter vacuum steel tubes inside. Remarkably, these facilities aren't co-located. They're 3,000 kilometers apart in the U.S. Northwest and Southeast. This separation exists because gravitational wave signals are incredibly weak. To eliminate noise or false positives, both detectors must simultaneously register identical signals. Besides the U.S. facility, Italy has Virgo Interferometer, also hunting gravitational waves. With this grand design, observatories detect perturbations thousands of times smaller than protons. Naturally, such precision suffers significant noise interference. Airplanes, car engines, even rainfall can cause disturbances. Once, the observatory received bizarre signals with untraceable origins. After exhaustive searches, they found crows pecking ice on main coolant pipes caused the disturbance. Later, the observatory redesigned pipes to prevent surface icing. The gravitational wave detection team involves thousands from multiple countries. After continuous optimization and attempts, this massive research team finally achieved a breakthrough. In 2016, scientists announced the detection of gravitational waves, and subsequently, the 2017 Nobel Prize in Physics was awarded to 3 scholars for their major contributions to this discovery. Having covered astronomers' daily work and observation equipment, let's now discuss a fascinating part of the book: the various challenges astronomers face in their work. Observatories are mostly built in remote areas, and operating large telescopes is extremely complex. Thus, astronomers' observation trips often encounter unexpected situations. Some sound downright bizarre. The book's subtitle uses astronomy adventurers to express the numerous hardships astronomers face. These challenges fall into 3 categories: natural factors, wildlife, and human factors. First are natural factors, the most common challenges. Although observatories represent advanced technology, they're often built in wilderness areas, inevitably facing brutal conditions like storms, snow, and lightning strikes. Lenses shattered by gales, structures collapsed by heavy snow, even staff struck by lightning, all pose serious threats to astronomers' work. Worse natural threats include wildfires and earthquakes. To minimize moisture interference, many observatories are built in arid regions, also prone to wildfires. In 2003, severe fires in Canberra, Australia destroyed 5 telescopes at a local observatory. The author personally experienced an earthquake.
In 2006, while studying at the University of Hawaii and preparing for observation, she encountered a 6.7 magnitude earthquake centered at the observatory, cutting all power and communication.
Sheltering in temporary refuge, she wondered if observation could proceed, her only allocated opportunity that year. There are even more extreme natural phenomena. In 1980, scholar Doug was observing when a nearby volcano erupted massively. Faced with such a disaster, this scholar showed exceptional scientific composure calmly writing an observation log. An observation log is a record scholars write after each observation, noting time, weather conditions, etc. That day, Doug recorded observation time lost, 6 hours, reason, volcanic eruption, sky conditions, dark and foul smelling.
Beyond natural threats, astronomers face another kind of trouble from wildlife.
Astronomers often share stories of animal attacks at observatories, like giant spiders crawling into pant legs, or even bear encounters. Animals also cause many problems for telescopes themselves. For example, a telescope in California, USA, lost data. A report later cited a red snake climbing onto the observatory's wires as the cause. Radio telescopes particularly fear small birds because bird droppings on antennas interfere with electrical signals. To repel birds, observatories use all kinds of ingenious methods. Some cover telescopes with protective nets, others use sound waves to scare birds away. A UK observatory reported a fight fire with fire tactic. A pair of wild peregrine falcons nested on the telescope support tower. With these raptors nesting there, other small birds dare not approach. Of course, human interference also significantly impacts observations. Operational errors while using telescopes are commonplace. For instance, damaging lenses, breaking equipment, or accidentally causing small fires. These are very common. Moreover, there are more severe accidents, even newsworthy ones. Emily records 2 such incidents in her book. The first in 1970 in Texas, USA, at McDonald Observatory. Yes, the victim was an observatory, specifically its 107-inch telescope. A drunken observatory employee suddenly lost control, determined to kill this telescope. The drunkard pointed a gun at the operator to lower the telescope's mirror, then fired 7 shots at it. Fortunately, the mirror material was resilient. Bullets only left small holes. This incident spread instantly through the astronomy community. Some mourned deeply, since the telescope had only been operational for a year. But the good news, though bullets left small holes, the telescope still functioned, losing only about 1% light-gathering capacity. Some joke darkly that the shooting downgraded it from 107 to 106 inches, a silver lining compared to another truly tragic event. End quote. In the U.S., Green Bank Observatory housed a 300-foot radio telescope, nearly 100-meter radio telescope over 20 stories tall, weighing 600 tons. 800 tons. Yet, on November 16, 1988, this telescope collapsed instantly into wreckage. Described as a ship breaking apart, investigators found the cause: failure of a support component called a gusset plate due to incomplete structural design. Thus, for large astronomical instruments, any small oversight can cause irreparable loss. Still, astronomers strive to counter natural threats, animal disruptions, and human factors. Scientists and engineers continually develop new technologies to explore the vast cosmos. Astronomical equipment evolves rapidly, with larger telescopes pointing toward distant space. Finally, we attempt to interpret the meaning of last in the book's title. Early astronomical observations required astronomers to travel to remote observatories, facing constant risks. They endured long nights by telescopes to capture coveted celestial images. The entire process was truly an adventure. Today, technology enables remote observation via the internet. New generation scholars observe stars by inputting commands from their couches, controlling distant instruments. Thus, traditional stargazing methods vanished. By calling them last stargazers, the author likely honors those telescope-side astronomers and their spirit of exploration. Inspired by this spirit, humanity has achieved feats from capturing gravitational waves to photographing black holes. In recent years, we've witnessed increasing astronomical breakthroughs, all made possible by innovative equipment and astronomers' dedication. Which astronomical discoveries have left the deepest impression on you? Feel free to show your thoughts in the comments section. Through personal journeys and professional insights, the author unveils the mystique surrounding astronomers in this book. In our vast universe, Earth is but a speck, yet despite challenges, There will always be those gazing upward, chasing starlight. All right, that concludes our exploration of the last stargazers. Find show notes below the audio. Until next time,